And in Cargès, we have beginning to make this kind of workshop nearly since 28 years about wave in complex media and all kind of things. And it was at one of these workshops that exchanging between people from seismology and people from physics, some nice idea came. And passive imaging was really something that begin here, in fact, through the work of Richard Weaver and Michel Campillo and Anne begin to see this, and with Nicolas Shapira, and from this new idea came. That is to say, it is a good idea to come here to learn and to think about physics or seismology. My talk is about ultrasonic imaging and noise correlation, and I will show you different things which are important to understand better the field of passive imaging and how the field of passive imaging can be connected to the field of active imaging. Let us begin first by basic physics. Why we can make an image from waves? It is in fact because waves has a very beautiful property. It is usually time reversal invariant. And because of this, it's not too complicated to make an image when you receive a wave field coming from some source. You can time reverse this wave field and go back to the source and in fact see what is the source. Let us come back to very basic physics. If you look wave, and here I put a wave which is a scalar wave, like acoustic wave, but what I say is valid if a wave is elastic wave, where you have something a little bit more complicated. But what is important in wave physics, if you are in a non-dissipative medium, that is to say, if the wave energy is not transformed in it, you know that the wave equation is written like this in a medium where the velocity depends of position. It's an heterogeneous medium. Here I put a source, the simplest one, a point source, giving just a pulse at one time t equals 0, and I look the wave field coming from this. And in fact, if I found a solution for this, I have my source, I send a wave field, and I look what is called the green function, because it is the source is a point. In this case, I look what is the field, and usually the field emerges from the source and diverge. And if, for example, I have some heterogeneity, the wave field, as it moves, is more and more complex, and it can have multiple scattering, like it was discussed just before. And here I show you the classical solution, which is the so-called causal solution. The field comes from the source, and it grows out of the source at time after the point, the initial time. But in fact, because of the second order time derivative and because of the property of delta function, there is also another solution which is as valid as this one, the so-called anti-causal function. If you have a wave field like this that begins before time t0, it will collapse to this point, but this is a mathematical solution as valid as this one if I look this equation. In this equation, there is no causality. There is only time reversal invariance. And it is strange that nobody sees this anti-causal green function. When I decide to send a wave field, nothing begins to, at the boundary of universe, to send me a wave before. This is anti-causal. And of course, in our universe, we say this one is not valid. But for a mathematician, it is valid. For a physicist, because we live in causal universe, you never see this. And now, if you want to make a time machine for waves, in fact, you ask, when I measure this causal green function coming from a source, because I am in a causal universe, can I build an anti-causal green function that exactly come back to the source? If I can do this, I can perfectly focus on a point, whatever is the complexity of the medium where I propagate. And this was a nice story that we were interested in my lab 30 years ago. And from this, we developed a first approach to create time machine for waves that we called time reversal mirror. And the time reversal mirror play on only what I call the boundary condition. I measure the field coming from the source on some boundary. It's a surface, a two-dimensional surface, and after I make a transformation. But there are two ways, in fact, to create time reverse wave. There is another way that I call the Loschmidt approach, and where I don't measure the field on a surface surrounding my source, but I just measure the field everywhere only at one time. It is not like measuring the field on a surface at different time. It is just instantaneous measurement of the field. And there is also a very nice way to create time reverse wave. And I will show you the two, and you will see there is a lot of nice physics on it. All this comes from the fact that when you play with a wave equation, and here I put, as I say, wave equation for a scalar field, but this is valid with polarization for any kind of field, you know that you have an equation that works on four-dimensional. My solution depends of space, 3 dimensions of space, and 1 of time. And you know that it is a second-order linear partial differential equation. And this has some nice property that was studied by a French mathematician, Cauchy. I think he was French and not Swiss. No, I think he is French. And that say the following. If you want to determine the field in 4 dimensions, you don't need to measure it in 4 dimensions. It is enough if you know the field only on the boundary of a 4-dimensional space. What is the boundary of a 4-dimensional space? It is a space with 3 dimensions. But how can you build 3 dimensions from 4 dimensions? Or you take 2 dimensions in space plus time, or you take 0 time and 3 dimensions in space. And these are what is called the Cauchy condition. They tell you that if you want to know a field at any time, everywhere in 3 dimensions, past or future for the time, it is enough to know the field only on an hypersurface. What kind of hypersurface you can have with 3D coming from space-time? You can have what is called the Cauchy spatial boundary. Spatial boundary tell you that if you know the field only on 2 dimensions of space, here 2 dimensions of space, plus the field at any time, t, but to know the field, because it's a second-order equation, you have to know both the field and what you call the normal derivative of the field. If you know this, you have enough information to find the field in 3 dimensions at any time, everywhere. This is what people call usually this diffraction theory. This is one kind of Cauchy condition. Now there is another way to create an hypersurface in 3D. It is to know only the field at one time. I call this time ti. And imagine that you measure the field at one time ti. You measure everywhere in 3 dimensions the field and its time derivative instead of the normal derivative. You have enough information to predict the field at any time after or at any time before. These are the two ways that allow you to manipulate wave field in 4 dimensions. 3 dimensions is enough, or BC, boundary condition, or IC, initial condition. Let us look first BC. BC, it's the old idea of time reversal that I called here time reversal mirror. I know the knowledge of a wave field along 2-dimensional boundary is enough to predict the field in 3 dimensions, plus the time, of course. Imagine that I have a source. Here I put a point, but in fact I can have any object that is a source. But what I show is important here. If I have just a point, I send a wave. It is the causal green function. And here I put on this boundary a lot of microphones, or geophone if you want. And in this case, I record the field coming from this point along 2-dimensional surface plus the time. And I record all this coda that I have here and I put in memory. I have enough information to recover the field in 3D. How can I play with this field? Because of the time reversal symmetry, I will come back on this. I can do the following. I can record on this boundary both the field and its normal derivative. In fact, it means that I need to have two kinds of microphone, one measuring the field, the other the normal derivative. One is what is called a monopole microphone, and the other one is a dipole. And it will be very complicated to record the two. But if I am in the far field of my source, in fact, the normal derivative of the field becomes proportional to the field. And if I am in the far field of the source, it is enough to record only phi. In this case, it's easier. I can use only one kind of microphone. And if I have recorded this field on the memory, now if I want to create the time reverse field, I have just to time reverse the chronology of what I receive. And now, in a second step, I will emit from this signal exactly in time reverse chronology. And now, if each microphone becomes a loudspeaker, it is what I call a reversible antenna, I will create exactly a field that will go backward, and it will be exactly the time reverse field. And even if the medium is very complex, it will refocus back. But there is a but. When you create a time reverse field, it's very nice. It comes back at the source. But because you have energy conservation, all this converging field collapse, and after it diverge. And this is very important because in a causal universe, nobody can create just an anti-causal green function. It will be always followed by a diverging wave. And this is because we are in a causal universe. Let us see this better. I send a wave field in a very homogeneous medium and a very in a pulse regime. I send this wave field. I have an observer. He sees one click when the spherical wave comes. This is the forward step. I have created the causal green function. Now I measure the field and I time reverse. Bon, this happened at the time tau. Now I time reverse. I send back, but because it cannot stop, I create two wave fields. One is the anti-causal, and when it's collapsed, the sign is changed, and the diverging wave is here with a minus. That is to say, a guy which is here, he will receive, during the time reverse step, two fields, one click, plus a second one when the negative wave comes back here. And this is something that reminds you something about when you are doing cross-correlation of between two signals, and I will show you how this is related to cross-correlation technique. But here you see what you have. Here I have used just a pulse. A pulse is very broadband signal. But now I can do the same with a signal which has some bandwidth. If I use, for example, a signal like this one, I come back just. When I do this, my converging wave diverge, and because it has some extension in space, there will be an interference between the converging wave and the diverging wave. And if you look at the collapse time, what you have exactly a focal spot, and if you look the size, it is half the wavelength. And in fact, when you do a time reversal step with some bandwidth, what you obtain at the focal point is not a singularity. It is because of the interference between the converging and diverging, it is a spot whose size is λ/2. And this is diffraction limit. And if you look this along axis Z, if you look during time how it behaves, time is here and space is here, Z, you see that when the annulus come, here you see them and you see when they collapse, and here there is the spot, and the spot has a size λ/2. λ/2 is the diffraction limit in wave physics. You cannot do better except if you play something that I can comment after, but in free space, this is the focus point. Now, all what I say is valid also if I use monochromatic wave. If I create a converging monochromatic wave, it is exponential minus gk/r/r. I want to create this. This has a singularity at the origin, but because I cannot create this only, after the collapse, there is also minus exponential gk/r/r. The sum of the two is an interference for a monochromatic wave, and the sum of the two is sinc kr over r. And sinc kr over r is a function that has a size which is lambda over 2. This is the origin of diffraction limit in wave physics. And here I see when the green function is written here, exponential gkr over r, here what I have here is the imaginary part of the green function. And you observe always the imaginary part of the green function when you play focusing, even with the best thing, which is a closed time reversal mirror. Here I show you what happens if I have a limited time reversal mirror. It is not a mirror that surrounds my medium, but if I have a mirror of size d, and if I have a source at a distance f of a mirror, it's like the focal distance, when I record the field and I time reverse it, it's come back, but it will not collapse on a point of size lambda over 2. It will collapse on a spot which is limited by the aperture, because I have not all the angle that I need to refocus from all directions. I refocus only from some direction. And when I look what I have here at the collapse time, I have this kind of moustache, and the size is lambda over f over d. This is not lambda over 2, it is bigger. This is usual physics. All of you know this, but it's better to come back to this for after. Now, this was a time reversal mirror where I measure the field on the boundary in space. Now, can I make another kind of time reversal mirror that I will call the instantaneous time mirror à la Le Schmidt, and I will explain why. And the idea is the following. Imagine that at one time, that I call TF, I measure everywhere in my medium, but I need to be a demon. I measure the field everywhere and the time derivative of field. I know all on my field at one time, field and time derivative. And imagine that I prepare after, at another time, Ti, new initial condition, where I create exactly the same field. The wave field is the same, but the time derivative I put a minus. And I create this initial condition. If I create this, it is exactly what I need to create a time reverse wave. Why? Because this is exactly like what Le Schmidt discussed with Boltzmann about reversibility in physics of particles. You know that Newton mechanics is time reversal invariant. And you know that if you have many particles at the time t0 that these are particles, it is not wave, that go in all directions in a box. If you look at time tf, where are all the particles? And if you measure the velocity of each particle, you know the position at time tf and the velocity. And now, if you prepare a new initial condition where you have reversed the velocity of all particles, and you send them, all the particles has to go in reverse, and they will come back exactly at the origin. This is called the Le Schmidt demand, and this is mathematically valid, except if you make any small error when you measure the position or the velocity of particles, all the small error will increase exponentially because of property of nonlinear property of the dynamic of particle. And you know this is chaos, but you can, in theory, recreate this. But now if you play the same, not for particle, but for waves, but it is like you reverse the velocity, you reverse the field, you are happy because wave equation is linear. And even if you make a small error in the preparation of your system, the error will remain small, not like if it is particle. But now, how to make a Le Schmidt demand for waves, but suddenly put a minus? Difficult. But there are at least two elegant ways to do the same. Instead of preparing a new initial condition for my field, which is the field and minus the time derivative before, I prefer, when I have my field here, I killed the time derivative. I prepare an initial condition where I have no more time derivative. I have just an initial condition, which is just the field itself, but it has no more time derivative. To do this, it is like I killed everywhere the time derivative of my field. The time derivative gives you what is called the kinetic energy of your wave field. And to create this, you have suddenly to create what we call the shock of dissipation. You have a wave field that propagates in a medium. Suddenly, up, you killed all time derivative. That is to say, if it is electromagnetic wave, suddenly you propagate in a medium, and suddenly you create a huge conductivity. And huge conductivity, it means big Joule effect, and it means I have no more time derivative. If you are doing this, preparing an initial condition like this, because everything is linear, it is the superposition of two initial conditions. Phi for the field and 0 for the time derivative. It is like I create here half the field plus half the time derivative of the initial field plus half the field minus half the time derivative. This is half the forward wave. If you are doing this, you send a wave in a medium, the wave propagates, suddenly up, you absorb the energy, and you see that a wave continues to propagate, but it is half the amplitude, and you see a time reverse wave. Okay, interesting. Now, not easy to do this, but you can do another thing. You know that at one time, you have a field and its time derivative as time TF. Now, if you are a magician, and you will see that we are a magician, imagine that suddenly you create a new initial condition, which is the same wave field, but you change just the ratio, you change the time derivative just by a factor alpha. Changing the ratio between the field and its time derivative, it is like you change the impedance of a wave, or the velocity of a wave. And I will show you how we can do this. If you are doing this, what happens? This new initial condition that you create at time ti is 1 plus alpha of phi. This is exactly the forward wave, but this amplitude, and this is a backward wave because there is the minus the time reverse wave. And it is like I create this forward wave, this and this. How to do this business? How to change suddenly the relation between the wave field and its temporal derivative? How to change? Well, the ratio of the field and temporal derivative define what is called the wave impedance. And if I change the wave impedance of my medium, or for many cases, it is the same than the wave velocity of what we call the refractive index. This must happen. Let us look this for water wave. Why water wave? Water wave, yesterday we have a talk on water wave, and here I will discuss just on water wave in shallow water with some elevation h. And I will just speak of linearized water wave equation, taking into account only gravity as the restoring force. And you know that if you look what is called gravity wave, in shallow water, if you linearize things, and if you forget capillary effect and viscous effect, you know that the wave equation followed by the elevation of your water is a kind of wave equation like the D'Alembert equation, and you have, in fact, a velocity C0 that depends of J, the gravitational acceleration, and h. And you know, if you send a wave in this medium, how can I change suddenly C0, the velocity? But in fact, it is easy. Just change gravitation. And if you are God, you can change gravitation very easily. Our God is Einstein. Einstein speaks of the equivalence principle in general gravity, in relativity, and he says that acceleration or gravity is the same. That is to say, if you just change, if you create for this bath a vertical acceleration with some, you can create a new gravitational acceleration, which is g plus the acceleration, the vertical acceleration you create. You can play by changing the apparent gravity just by creating vertical acceleration of your bath. Okay, let us look how we can do this. We have a bath, it's a water tank. We have a big shaker here, and we send a source. A source can be any object that creates a wave field. And this wave field propagates, and suddenly, puff, we will create a vertical acceleration. Usually we create, it is better to create a vertical negative acceleration. or it can be positive or negative. And when you are doing this, the gravity acceleration go from g to g plus gamma t being the acceleration you give to your bath. And if you are able to do this very quickly compared to the periodicity of the wave you are sending in the medium, you will create what I call a shock of refractive index. In a small amount of time, you create your alpha that exists just during a small amount of time at TF. If you play with this, well, you have your water tank here, you have a big shaker and the water tank, and you play with this, and you send a wave, any kind of wave, and suddenly you will move your bath vertically, but in a negative direction with minus 20 G. Well, it is fast. And you do this during a small amount of time. And now you look the movie. This is an Eiffel Tower, small, that fall in my bath, is give a wave field, and suddenly, up, I create a shock, and what you see in your bath is an Eiffel Tower that is coming back. And you see this, oh, strange. Bon, if you are not sure, you can play with a smiley. You do this, check. Okay, it works. And here it is quite strange. It tells you that in the pattern that come from any object, if you look the pattern at one time, and if somewhere you reverse the time derivative, you have the memory of all your initial object, and you see the object coming back. It is like holography, but in holography, you are measuring only the wave pattern coming from an object on a two-dimensional surface. Here, it's an hologram in the time domain. It is the fringe that are moving, and suddenly you do this. Well, okay, this is nice. I want to show you this because this is not usual. If you can do this on water wave when there is a big earthquake or kind of tsunami, perhaps you can see that water wave go in reverse if you create a vertical event. I am not sure. I asked to Jean-Paul Montagnier if he has not a satellite image coming from all the structure of waves during a very big events like the one in Indonesia where there was a vertical acceleration which was tough. I don't know if anybody has seen this, but this is in fact interesting. Now, let us look just for a point. In fact, the wave that we have here are not only gravity wave, because we play a small scale, we have also capillary effect, and in fact, the wave you send is in fact dispersive. And in fact, if you look, the wave is dispersive, you make your shock, it's come back, and because I don't stop the movie, you see that the wave come back, collapse, and diverge again. And you see that during the collapse, you have this diffraction spot that appears here. Okay, forget this. Now, this is basic physics. Now, I want to show you that this basic physics explains why you can extract green function from ambient noise. And I want to show you the time reversal point of view. Let us come back to the time reversal mirror, the one which has many antennas all around the medium. And I want to show you this analogy, which is very strong. You know that if you have a source, a point source, sending a wave, if you have a complex object made of reflectors, and if you have one antenna that records the field and that you can move, you can record the causal green function, which is what you emit, but you receive at any point, taking into account all the interaction. There can be multiple scattering or anything. Well, this is what you want to measure. But this needs an active source and a passive reflector. Now, now remember my formula at the beginning of my talk. Imagine that you have a source at point R0 and you have a lot of antennas that surround the medium. Source at point R0, send a click. It goes through a medium where you have obstacles and you measure the wave field on each point. Now, when you have measured the wave field, in the second step, you time reverse this wave field and you look what is the field that you create back. And you remember we found this But this was for homogeneous medium. We found that the wave field that is created by the boundary is the time reverse of the causal green function minus the time reverse of the anti-causal minus the time reverse of the causal. And in fact, this theorem is valid whatever is the complexity of the medium. When I show you this in free space, it was obvious. A diverging wave comes back as a converging wave, and you understand all the limits. But the theorem is perfectly valid whatever is the complexity. This is a universal theorem that can be demonstrated en 2 coups de cuillère à peau, mais je ne le ferai pas là pour ne pas vous assommer complètement. When you have this is a time reversal experiment. The source was here, I measure the field, I send back, and if I follow the field at every point R, it is written like this. Now, there is a complete analogy between the physics of this experiment, which is a time reversal experiment with a source at point R0, and another experiment. Instead of having antennae that are reversible on the boundary, I have here only noise source. I put on each point noise source, and I send white noise, which is without any correlation between all these sources. And I have the same medium with the same obstacle, and I have here 2 guys that are 2 receivers, 2 passive guys, instead of 1 active, 1 receive, 2 passive. And I measure the correlation between the 2 signals they receive, and I put a time derivative of this correlation function, and mathematically, I found this. This is exactly this. And why I have this? This I understand from where it comes. This, it's not so obvious. And this I will explain you very quickly why, but it's interesting. If I do only, I have a source at point R0. A perfect time reversal mirror needs to have antenna everywhere. But imagine that I have only 1 antenna at point Ri. My source sends a click, it goes through this medium, I record on Ri. This is what I call the one-channel time reversal mirror. I record here G of Ri, R0. Don't forget that I have what is called spatial reciprocity. If R0 sends something on Ri, R0 is here, it's the input, the output is here, but in fact, if I reverse, I have also spatial reciprocity, and I will come back on this. I have R0, Ri. Now, I take this, I time reverse this, clack. And now I send it back from Ri, and I look to R. I have exactly, I send this as an input here, and it has to propagate, and it will be convoluted by the impulse response between Ri and R. And because I have a convolution that creates a dimension of time, I have to put a time derivative here plus a constant. When I do a time reversal experiment with only 1 channel, I send something from R0, what I will have on R will be this. Okay, this is time reversal on 1 channel. It is not a perfect time reversal. Now I can compare this experiment to another one. I have a source at point Ri. It is first a Dirac source. I send just a click. And I have 2 observers, one at point R0, one at point R. And when I send my click here, Dirac, here I will receive a coda, and here I will receive a coda. But it is only a coda due to the multiple scattering in my medium. It is not noise. It is due just to the geometry of my medium. And I can compare what I receive on guy R0 and guy R. And I can make the cross correlation, the intercorrelation between these 2. And it will be 1 green function with minus convolute by the other green function with T. And this is what I receive. This is not very far from this. I have spatial reciprocity, but it allows me to change Ri and R0. And if I look, I found that the time reverse wave that I have when I have a time reversal mirror of 1 channel and the correlation between the signal received by this point, they are the 2 related like this. But here, I have only a 1-channel time reversal. What I want is to have, not to send a Dirac pulse first, I want to send noise. if I send from point RE noise, if I compare what R0 and R receive, and if I send a white noise, the cross correlation will be this noise convoluted by the impulse response on one channel, and the noise convoluted by the other impulse response. And because the two are completely uncorrelated, the result is that the spatial correlation between the noise received by these two observers is written like this. Okay, nothing new. The noise correlation recorded by two observers give, and because I have a formula just before, give within a time derivative the same result than a time reversal experiment conducted with one channel time reversal mirror. One channel time reversal mirror is not enough to do all the play that I want to do. Now, instead of having only just one source of noise on one point and making the correlation, I add other source of noise, which are incoherent all. And I add many of them, like if I have source that surround the medium. And I will go from a one-channel time reversal mirror to a full channel time reversal mirror. And I look what are the signals I receive on my two antennas, and I have to make the summation of all the position of all my noise source that surround the medium, like in a time reversal mirror. And because I have my formula here that tell me that the correlation between these two noise is at the time derivative the same that the time reverse field, I know what is the time reverse field of a full time reversal mirror. It is G anti-causal minus G causal. I put anti-causal here. If I put causal, there will be a minus. And I found suddenly my theorem. My theorem tells me that the cross-correlation between these 2 points coming from a noise coming from all directions, it is like I have a perfect time reversal experiment. And the connection is very strong. And in fact, the connection is strong. It is a demonstration of the main theorem you use. Usually, you prefer, when you are thinking of noise coming from all directions, you prefer to say that the noise is coming from all points in the medium. Here, I just say that if you have source coming from all directions on a surface, if they are incoherent, you create by cross-correlation, you measure the difference between the two green functions. And in fact, this is interesting because this allows you to do the same, to do the following. Here, I speak of U in, U out. It is the position of two receivers, two antennas. And I have an obstacle, and what I understand is that if I surround these two antennas by noise coming from all directions, if I measure the noise on these two antennas, if I cross-correlated, this is what I just demonstrate, I found the direction between the I found the green function between U in and U out with this minus term. And you know all this. This is all on what is based passive imaging. And for example, if here you have two antennas, and here you have some obstacle. What you will find when you do the cross-correlation will be not only two peaks that correspond to the wave coming from U in directly to U out, but you will also see the peak, the path coming through each obstacle. And here you see that if you do a careful measurement of the cross-correlation between two receivers in noise, if you have a complex structure, the complex structure information is put here. And in fact, it tells you that when you are doing this carefully, by doing enough average to extract the green function, you have not only the speed of your relay wave or any kind of wave, but you have also information of each obstacle in your path. And you can play with this, and you can, from this, deduce what we call the reflection matrix. The reflection matrix is a tool that I will explain now. That is a tool that we used in ultrasonic, in medical ultrasound, where we have many antenna, not 2 antenna, but typically 256 antenna, and where each antenna emit a signal, each other receive a signal, and we measure what we call the reflection matrix. And in fact, what you see is that with ultrasound, we have no problem to measure in an active wave the reflection matrix, but in seismology, it is better to measure the same in a passive wave. And this is what Alexandre will show you tomorrow, how in some volcano, by using many geophones and by using the noise, he can extract all the Green's function, and from this, he will go in the reflection matrix theory. And the reflection matrix is a fantastic tool to make an image. And now I will go on this part, 11h20. Okay, this is the classical thing that you know, when you have no obstacle, you just found the velocity. But now I go to ultrasound imaging. Ultrasound imaging, well, I use array of piezoelectric transducer, typically 256 transducer, but I can control them actively. Each are transmitter, each are receiver. I can do what I want with them. The basic way, when you use this and you put the probe on the body, is to use frequency of the order of megahertz that give a millimetric wavelength or submillimetric wavelength. You send this. But usually, when you want to make an image of the reflectivity of the medium, you learn how to focus wave in the medium. And to do this, you have to make an assumption. I know the velocity of my ultrasonic wave in my medium. And usually you make the assumption in all systems that the velocity is the same everywhere, 1,520 meters per second, like in water. And you decide that you know the velocity. And to focus a wave, to create just a small spot, you send from each transducer electrical signal with some delay. By using Huygens principle, you add them. This is focusing in transmit. And now if there is a target, a reflector, you can also do the same beamforming in receive. You receive all the echo, and you put delay. And if you put delay to compensate the curvature, you create a plane wave, and you add, and you have a very strong signal. And you do what is called double focusing. I focus in transmit and in receive. In optics, people call this confocal imaging. You make double focusing, but this does not give you an image. It gives you only the image of a small zone where you have focus. To make an image, you have to send a first beam, listening the echo coming from a small zone. Here it's the depth of focus of your system. And after you create another beam, another beam, another beam, another beam, and you change the focal distance. And at the end, you have an image. And it takes some time because you have typically to create 1,000 beam, focus at different positions, and you have to take into account the velocity of ultrasound to see how long it takes. And typically, you make 50 frames per second. It's not bad. And now, when you look at an image, and this is depth, and this is this direction, you see layer. This is the skin and muscle, and you see after a noise. And you see vessel, and you can see many structures. But you can see many different things. You see that you have an abdominal layer, and for many patients, abdominal layer are aberrator. If you are very muscular, or if you have very fatty, fat has not the same velocity than muscle, muscle has not the same velocity than liver, and you begin to create lens that create aberration. And you see also that you have this noise coming from all the structure. And this noise comes from the fact that we are lucky in medicine. The body is full of small scatterers. Each scatterer is a reflector. And you have a random distribution of scatterers. These are due to the collagen of tissue. And you have this noise. And sometimes you have some bright point scatter. If you want to look on a breast phantom, on a breast, you want to find if there are microcalcification. These are bright spots, and you want to be sure to know how many bright spots you have. And images are often very poor because there are aberrators. You don't know the exact velocity. How can you play with this? And here is something very interesting that I want to show you because I don't think you know the van Sitter-Zernike theorem. This is something interesting. If you focus not on one point scatter, you are lucky if you found one point, but usually you focus on a distribution of scatter which are randomly distributed, and you focus with a focal spot which is quite bigger than the distance between each scatter. It is like you focus in a heterogeneous medium whose scale are smaller than the size of your focal beam. What you are doing is the following. This is an old story that we studied in 91. Some of you perhaps were not born, but it's quite interesting. You have your array of transducers. You focus. Bon, easy to focus. And here there are many scatterers. And you listen the echo. And when the echo comes back, you compare the noise you receive on each channel. Usually, in the system, we don't do this. In a medical system, you focus in transmit, and in receive, you focus. You do what is called beamforming. You don't see each individual signal. You forget them, you add them with delay. It is what is called double focusing. But here, you look each of this noise. And you decide that it is noise. Oh, what is the spatial correlation of this noise? How is the noise on one transducer compared to the noise on a closed transducer? And you can, because you have put some cylindrical focusing or spherical focusing, you can now put the same delay that the one you used and compare the noise you receive in each channel. And you can measure the cross correlation between each noise received on each antenna. And if you measure this, you can do a cross correlation of this time series, and you can make a cross correlation that you normalize to 1. That is to say, you compare is it similar the signal on channel 1 and channel 2, or channel 1 and channel 3, channel 1 and channel 4, and you do this for all, and you average this. And when you are doing this, you see something very funny. If you have perfectly focus on the medium, that is to say, if you have created from your aperture a focal spot whose size is exactly lambda f over d, like if there is no aberration, it is a sinc function when you focus. If you have created this, you see that the noise you receive on each channel has a spatial correlation. Here it is what you receive. When you compare one channel to the other one and to two, and you change the pitch, you see that it is a triangular function that decreases with distance. This one and this one are very close. This one and 2, 3, 4, and you see that it decreases to reach exactly at the from this one and to this one, there is no more correlation. And you can measure this spatial correlation. And when you see this, it's a very interesting thing. You see a triangular function for the spatial correlation. And mathematically, if you look this, it is exactly the Fourier transform of sinc square. If you have a sinc function, you can do the Fourier transform. It is a rectangular function. And if you have a sinc square, that is to say the energy you have in your beam, the Fourier transform of the sinc square is a triangle. And you see that there is a fantastic theorem. If you have well focus in the medium, you have created an incoherent distribution of noise coming from the medium, but it comes from only this size, which is the focus size. And when the correlation of this wave field propagate, when you look at it, it's a triangle function. Why? This is related to something very important for astronomers, how to measure the diameter of a star. You know that Young experiment, when you put two holes here, if you send light, a monochromatic plane wave, you send a light and you have two Young holes. You know that you will see fringe appearing because of interference between what comes from here and here. This is when you send a plane wave monochromatic. This is fringe. You know all this. But you know something very interesting. If you look the light coming from the sun, put a screen with two holes. Put two holes at 1 centimeter, one from the other, and look if light coming from these two holes coming from the sun, did they create fringe? No. This is 1 centimeter. But now, take one point and the other and make them closer and closer. When you are at 0.8 millimeter between these 2 points, the light that comes from these 2 points is coherent. And here you will see fringe. And you know that it is a way to measure, when you have an interferometer, the size of an incoherent source. And this is quite nice. If you have a large incoherent source, the field that comes from this incoherent source is completely incoherent at the origin. It's the white noise. But as the white noise propagates in space, it becomes to get more and more correlation, because propagation is a low-pass filter for spatial frequency. And when you are moving, here the source was big, the two sources give me no fringe. But when the source becomes small, the source gives me fringe. And if you know the distance between the sun and the Earth, 150 million kilomètres, and if you know the diameter of the sun, you will find 0.8 millimeter for the cohesion length of the light coming from the sun. And here, you have this beautiful theorem. Oh, sorry. The spatial correlation of a field propagates. You have a field, it has some spatial correlation, but the field comes from a limited aperture. It is not noise coming from a huge aperture. It comes from a source, which the spatial correlation propagates, and when you observe it, it is the Fourier transform of the incoherent source aperture. This is the Van Sitter-Zernig theorem, which is a fantastic theorem and very useful. And here, what we are doing, you focus. If you focus well, you create a source of noise coming from a zone whose size is lambda f over d and whose shape is sinc. A sinc, if you have this. Now, if here you have a random distribution of scatter, it is like you put a random mirror here, and now the scattered field will be the incoming field multiplied by this random mirror reflectivity. And now it is what is coming back, and now it has to propagate. And when this random field propagates from this plane to this plane, you have to use diffraction theory. It may be what is called Fresnel transform or Fourier transform. It depends what distance you are. And when you look now at the noise, the spatial correlation is not the same, but the spatial correlation here, it has moved. And when you look at it, the theorem tells you that the spatial correlation is just the Fourier transform of p square, that is to say, the energy distribution you have in your medium. And this is what you obtain when there is no aberration. You have focus well, and just by sniffing the echo, you can say, I have focused well because I found that my spatial correlation is a triangular function. Now, what happened? This is when I focus well. Now, I have all my signals are very similar, and I measure the spatial correlation, it's this. Now, imagine that I have an aberrator, and it can happen when you do in the body, you have aberrator everywhere. And now the field is very large. And now if you just measure the echo, you see on the echo that the spatial correlation, if you measure them, it's become not as wide. And you see that you have a signature of a medium where your focus is not well done. You know that because the spatial correlation is not a triangular function, you have not focused well. And if you see that the size of this become much smaller, it is the Fourier transform of your focal spot. And you can measure, in fact, the focal spot you create in the medium without being in the medium. You have not to have hydrophone in the medium to measure. You just listen the echo. And you see that the spatial correlation change. Okay. Now, what is the difference between the echo from a point scatter? If you have only a point scatter, you send a beam. If you have only in your medium, you don't know what you have, huh? But if you have just a point scatter, all the echo are the same. And if you do the spatial correlation by correcting from the sphericity, you will have a spatial correlation which is 1 everywhere. When you compare this to this, it is 1. It is a flat spatial correlation. This is the signature of one scatter. But if here you have a distribution of scatter, the spatial correlation will be not 1. It may be a triangular function. And if there is some aberrator, you will see that it's changed. Okay. In fact, you can define what we call the focusing criteria. You begin to focus in a medium, and you listen what comes back. You have all your echo, and you can add them through the delay you used in transmit. And you create what we call a coherent echo. And when you compare the coherent echo is the sum of all this signal with a delay you need to focus initially. But you don't know if you have focused well or not. But you have done this and you have a coherent echo. You can compare what we call the coherent energy. That is to say, the energy in the coherent echo. You take the square of this, you integrate, and you have an energy. But you can compare this with the energy you have in each channel. But each channel are uncorrelated, are not perfectly correlated with the other. And you can compare the coherent energy coming from a zone to the incoherent energy, which is the sum of all the energy coming in each channel. And usually, if you have a random distribution here, because you will have this, and if the distribution is random, and if you have well focus, what we call the C factor will be equal to 2/3. That is to say, when you focus somewhere, you listen what comes, you compare the energy you have in your coherent echo to the energy you have in each channel. And if the ratio is 2/3, you know that you have a perfect random noise. Now, if you have a point, the same factor, say, will be 1. And if you have now a medium where you have aberration, it will be not 2/3, it will be less, smaller. And you can play with this. And you can focus everywhere, you listen what comes, you measure this coherent factor that tell you what are the spatial correlation, and it tell you what kind of medium you are looking in your beam. And you can see, oh, this is not a good medium, this is really strongly aberrated, for example. Okay, let us go one step more. Now, I want to speak of time reversal in pulse echo mode, and I will introduce the reflection matrix and the time reversal operator. And you will see that all these connect together in a huge theory. Okay. You know that the problem is aberration. When you have aberration, you don't know you have a piece of aberrator that is not really good for you when you want to focus. Imagine that you have only one scatter. Imagine that you insonify it with a beam coming from one transducer. It's common the scatter, and the scatter gives an echo, and the echo, when it's come, it goes through the aberrator, and the echo is distorted. And if you have only one scatter, if you just receive this wavefront, you time reverse it, you know that up, you have perfectly converged toward this point. You know that this wavefront has exactly the phase, the amplitude, what you need to focus on this. This is easy because you have transformed one passive target in one secondary source, unique, and you time reverse. Well, this is perfect time reversal to focus on a target and to destruct it, for example, if you want. Now, if you have more than one target, if you have typically two targets, but what I say is valid for many targets. If you have two targets which are at a distance bigger than the focal spot of your time reversal mirror. And here I have not put aberration, but what I say is valid with aberration. You transmit a beam from one antenna. You have two targets, two echo. You receive two echo, one strong from the strongest target, one weak from the weakest target. You receive this. You time reverse. You send back two waves, one strong on the strong target, one weak on the weak target. And if the distance between the two targets is bigger than the size of your focal spot, you can continue to play. you send something which is stronger and stronger on the big target and weaker on the small target. And you have what is called a power law. And after doing iteratively this, at the end, you focus only on the strongest target, the weakest disappear from your knowledge. And you found what I called the first invariant of the time reversal operation. This is the wavefront that exactly match this target. And this is an invariant of a time reversal operator. And the time reversal operator can be written as a matrix, as an operator. And the invariant of an operator are the so-called eigenvector of an operator. And once you know this, you can, of course, subtract this to learn now how to focus on the second target. And you can play. And if you have many targets, you can play with this. But this takes time. But whatever, we develop technique to play with this. But this is not too mathematic. Now, you can, with this idea that each target, if it is well separated to another target, correspond to what I call an invariant of a time reversal operator, you can ask, when I have a complex medium made of many targets, how many invariants I have? That will tell me how many bright targets I have and what are the wavefronts to focus on each of them. And to do this, you can use the reflection matrix. In the canonical basis, I explain myself, I have an array of transducers. Each transducer can transmit and receive. The position of each transducer is U in or U out if I transmit and U out if I receive. And I can record, because everything is linear, invariant versus time, I can take my time, I record all the inter-element impulse response between each transducer and each receiver. And for each U in, I have a U out. And because it is pulse echo, I have a time series that corresponds to all the echo coming from all the structure. And I can build a big matrix here for each transducer. Here I look. For each U in, I excite this one, this one, this one. And for each transducer, I look in the time domain what I have. And I record a mass of data. And from the full measurement of this, which is active here, U in, emit, U out, receive. When I have my data, I can select a time window. I can say I am interested what is at some depth. I select the time window, and now these are a kind of matrix of function of time. I don't like to manipulate function of time. I prefer to go in the Fourier space. And when I take all my data in one windows, I Fourier transform them, and now I have a matrix of complex number. R is made of complex number for one frequency. I have many frequencies, but for one frequency, for each U in that emit, I have a response of U out. It's a complex number that has a phase and amplitude that take care of all the business that I have here. And when I have this reflection matrix, I ask, what can I do with this reflection matrix? And I will show you that the singular value decomposition of this matrix is very interesting. The number of singular value I will have will give me the number of targets I have in my medium, and all the singular vector will be perfect focusing on each target. It is when I have many targets which are distant from more than the size of a focal spot. Why? Now I have, instead of speaking in the time domain, sorry, what I have done.
Attends, j'essaye de voir. Bizarre que j'ai réussi à faire ça.
Ça marche là? Oui. OK, I come back. OK. What I say, I send short pulse. I listen the echo with all the multiple U in, U out. Now I create a matrix R at one frequency. Now, this matrix tells me when I send from each U in what I receive U out. I can now go at one frequency. If I have an input vector E, it is just a sinusoidal wave that I put from one E. I send on my medium, and I listen what I have. I receive on each channel, this is monochromatic at one frequency, I receive R multiplied by E. The response of this medium is R multiplied by E. Now, when I do a time reversal for a monochromatic wave, it is like making phase conjugation. I send back R conjugate, E conjugate. I send back this. This is my time reversal step. I send in the medium. And now I have R star. And now I see that all this, I receive echo, I time reverse, I receive again. It is described by the operator R star. This is an operator. R is a matrix which is symmetric. Why? Because U in, U out can be reversed because of spatial reciprocity. Therefore, R star is Hermitian. An Hermitian matrix has eigenvector and eigenvalue which are positive and eigenvector which are orthogonal, and you can play with this. What are the invariants of a time reversal operator? In fact, if you measure this matrix R, if you have R star, if you make the diagonalization of R star, it will tell you how many on the diagonal, what are the... I record this, I have this, I make the diagonalization. I have here the diagonal matrix. The diagonal matrix has eigenvalue. The biggest one corresponds to the strongest target in my medium. The second one corresponds to the second target. And just by doing diagonalization of R star, I can find how many targets I have, and I can find what are the eigenvectors to focus on them. But instead of working on R star, if I know what is singular value decomposition, I know that the diagonal matrix correspond to R star is the same that the singular matrix correspond to R. And I can play this, and I can do a singular value and singular vector. And this is nice, because take an array, put some aberrator, put two targets here, and ask and measure the reflection matrix. Look how many eigenvalue you have. You have two big eigenvalue compared to 120 because you have 120 elements. And for each eigenvalue you found a vector, an eigenvector, which is exactly what you need to focus on each target. And this is in the case of two targets. Now, for example, if you have a phantom that mimic microcalcification, if you do classical imaging, it will be very difficult on the image to count how many microcalcification you have. But if you use the Dort method, it will tell you that there is 8 eigenvectors, and each of them focus on each target. And you can begin to discriminate through speckle noise what are the bright targets. Okay. Now, this is nice. But you have not only in the body big target, well-defined. You have a set of them, and it's interesting. But you have also this random noise. You have random noise plus target. How can I play with this? I can do what I called the focusing matrix approach. You remember, initially I have a matrix that relates U in to U out. Each element emit position U in, each receive at U out. This is my reflection matrix in what I call the canonical basis. It is the basis where I have my transducer. But you know that when you have an operator, you can write an operator in different bases. You can change bases to go from one basis to another one, and sometimes it is better. And here I will speak of focusing matrix. Now look, imagine that you have random noise. You focus on it with a focal law like I showed before. And you listen what are the echo coming from this zone. These are this echo, these are noise, but the spatial correlation of the noise is not so nice. You remember, if I measure the spatial correlation, it will be not a triangular function. It will tell me that it changed quickly. Now, you have focus here, you receive this, and you can iterate time reversal. And you ask, if I iterate time reversal, did at the end it's focused on a small spot? You have to iterate 1,000 times. Why? Before it converges. Why? Because here you have not two nice, well-separated spots. You have a random distribution of spots in one focal spot. That is to say, you have, and when you play, iteration does not converge or converge very weakly. And in fact, what you want to do is you want to field the spatial correlation, and you show that it is not nice, and you want to improve it to find the best law, to focus, to have the best spatial correlation at the end. When you have exactly reshaped your wavefront, you will be happy. Okay. Now, imagine that you are in free space, you have in a medium where you know the velocity. You focus on a position that I called R in, and you listen the echo that you have on each U out. Now you create a matrix where you have focus here and you have record on each. Now the input is a focus point that you think you have created, and the output is the response of your transducer. And now you move the R in to another position, And for each focus position, you listen the echo you have here. And you move R in at another position, and you have a new kind of matrix. It is like you have all your U outs in receive, but in transmit, it is like you have created virtual source of acoustic wave or seismic wave inside the medium with this series of focal spots. Now, if you look the new matrix you have, which is R in as an input instead of U in, but it is a focal spot created by a family of wave, you have this matrix that I call R in, U out. And now you time-gated and you make a Fourier transform, and you have a new set of complex number where your matrix has as an input all the focus position in the medium and as an output all the receiver position. And this matrix, R, you create the time reversal matrix of this. It is R multiplied not by R conjugated, but R transpose conjugated. Why? Because in fact, it is a matrix which is not square matrix. The number of R in and the number of U out are not the same. And you create a cross-correlation matrix. You have record the matrix of noise when you focus at different point R in your medium, and you create your cross-correlation matrix. And if you look, what is the cross-correlation matrix you have here? Each element of this cross-correlation matrix, which is what we call the time reversal operator, is the cross-correlation of received signal on transducer M and N when you have focus in some zone and some other zone. And you create an average of the cross-correlation along the transmit beam. And when you are doing this matrix that you found, which is the time reversal operator on a random distribution of scatter for a focusing matrix, become a triangular matrix. That is to say, R, the reflection matrix from this random noise, is a random matrix because it's noise. But when you create R dag, the cross-correlation matrix, it is no more random, and it's become, because of the Van Sitter-Zernig theorem, a triangular matrix. It is interesting. You play with random matrix, because when you focus in a random distribution of scatter, what comes back is random. But if you create R star, and if you have well focus, R star is no more random, it's a triangular matrix. But if you have not well focus, you see directly that R dag is not a nice triangle. You know that here you have some mess. And now your problem is, how can I automatically create a perfect focusing in this mess of random distribution? And in fact, to understand this, you have to understand the following concept, which is the isoplanetic patch, like you have in astronomy when you try to improve the image of a star. You know that the wavefront you need to focus perfectly through an aberrator is some wavefront. It is the geometric wavefront you need to go there, plus an aberration law due to this. And you know that it exists a small angle on which, if you want to focus to other zone, you will go through the same part of the aberrator, and for each point in this zone, you will have the same geometrical diffraction which change in direction, plus the same aberration, because you go through the same aberrator. And in fact, you see that a random distribution of scatter can be seen in the isoplanetic patch through the same aberration law. And because of this, you can do statistical average, and you can do the following. You are in front of a breast or liver of any patient, and you have to decide from this complex medium how many isoplanetic zones I have. That is to say, when I learn how to focus here, I want to be sure that my law to focus is valid on some patch all around. I don't want to, for each point, to create a perfect focusing. You have to divide it in a certain number of isoplanetic patch. For each isoplanetic patch here, for example, in all this zone, at the end, you will find an aberration profile that you have to correct for all this zone. For another zone, you will have another profile. You have to count this automatically. And to play with this, what you have, you begin, theta in. I put theta in here without introducing theta in. Okay, well, it's not, sorry, I will not kill you. No, but forget the theta in. Non, ça c'est, this is the fault of Alexandre. Now here, instead of putting theta in, I will put R in. And it tells you the following. If you focus in some zone R in, and you listen the echo here. If you focus on a R in which is a little bit shifted, but in the same isoplanetic angle, you will have another signature that will have the same aberration profile plus a different geometric profile due to the angle. And when you record the R in U out matrix, you will have for each R in different wavefront. Each wavefront is the sum of a geometrical wavefront that you know, plus an aberration, and you treat this signal, you treat this signal, and you just create a new matrix that we call the distortion matrix that Alexandre introduced. And this matrix contains for many zones around in one isoplanetic patch, it contains many profiles. Each of them are noisy, but each of them contains the same signature of my aberration. And I have to extract this. And for example, you focus here, you listen all the echo, and you put here a column of your matrix. For the first R in, you have a column of number, which are complex number. Now you focus at another position, you have another column. It is a new realization of noise, but you have shift, but you are in the same isoplanetic angle. And when you have this distortion matrix for many input, many R in, you can say what I have in memory between all of them. What is, can I extract the wavefront? And to do this, you have just to take this matrix, to make a singular value decomposition of this matrix, and it will give you an estimate of the aberration law. And you will find what is the good focusing for this zone. And you will have transformed a medium made of many random scatter is a medium like you have bright star. You know, when you want to focus in astronomy, you need a star on which your many mirrors are moving to focus better on this. And here, we have just random noise, and we extract from this random noise, which has a bad spatial correlation at the beginning, we extract something to converge, to make like you have created a bright star in a medium which is not one scatter, but which is a random distribution of scatter. You transform a random distribution of scatter in a bright star, which is like a big scatter. And we call this a virtual reflector. We transform, and when we play with this, what we do is in fact strongly related to time reversal. Remember, this is nice, but I don't know if I am, it will be the end of my talk. Huh? Is it good? Okay, yeah. I explain, sorry. I explain you that when I try to iteratively focus in a random distribution of scatter, if I focus always at the same, I will never converge. But if I focus here, and after if I move my focus point all around, and if I take all this data, making with them a matrix that I call the reflection matrix, if I take the SVD, it will give me exactly at the end what I need to focus on a virtual reflector, which is only one point. And we do this, and when you are doing this, it's nice because at the this is very time reversal related. I will not explain you all, but in fact, at the end, you can transform completely bad image in good image. Here it is a breast image. The image is completely poor. There was microcalcification structure that you don't see, but by measuring this matrix everywhere and playing with this, you obtain this. Okay, I think I have no time, but just to tell you that all this idea came and we applied them in a company we create from the lab, Supersonic Imaging, because Supersonic Imaging is the first company which is in Aix-en-Provence that creates a way to make ultrasonic image which is not confocal imaging. You focus here and you focus in receive and you move it. But we were the first company to create plane wave imaging. And plane wave imaging, it is nearly, it is this idea. You want to measure a reflection matrix, but if you send from each transducer a signal and receive from the other, you have a very bad signal to noise. We prefer to use all the transducer in to send plane wave. Like this, you put a lot of energy in the medium, and we send one plane wave, and we listen on each transducer what come back. And after we change the angle of the plane wave, and we say, and we send a set of plane wave with different angle, and for each of them, we receive on each transducer the signal. And in fact, we receive also a reflection matrix, but with a basis which is different. The input are plane wave, the output are transducer. And when this is very good on the point of view of signal to noise. And from this, we can combine all these plane wave that we receive and put in memory to mimic in the computer a matrix where we focus at every point Erin in the medium, because it's enough to combine different plane wave with different angle and phase to mimic focusing in transmit everywhere. And from the plane wave matrix, which is the faster to obtain, we need only 40 shots, and 40 shots, it means we can make nearly 500 images per second, which is ultra fast. We get all the reflection matrix by sending different plane wave and recording on each transducer. We put this in memory. And after, in the computer, we make transformation of this matrix to mimic focusing in point Erin here, in point Erin here, and we try all the algorithm. And we have, in fact, 3 different bases in transmit for the reflection matrix, or we use the canonical basis where each transducer emit, each receive. This is the canonical matrix, but it is very bad on the signal to noise point of view. This matrix plane wave is very good on signal to noise point of view, and it's ultra fast because you need a small number of angles. And you can also have a matrix where you focus physically at each point Erin, but it's very time consuming because you have to focus at every point. And we prefer to come back to begin with this, which is what we record. And from this, we deduce this, and after we can play and do all algorithm. And tomorrow, Alexandre Aubry, which is here and preparing his talk, will show you that because you can record the reflection matrix without active transducer, but because of passive imaging technique, we can play on the reflection matrix in very complex medium. And here I describe a medium where I have only 2 kinds of things. I have aberration, I have scatters, and I describe only random scatters where I have only what we call single scattering events. That is to say, when I send a beam, each scatter is small enough to send back only one beam, but there is not multiple scattering. And if there are multiple scattering, like what you show before to explain the coda, you will have in the reflection matrix the signature of both the noise coming from single scattering plus the noise coming from multiple scattering. And you will see that the noise coming from multiple scattering has a very peculiar signature. And from the reflection matrix, you can take it out and see deeper in complex medium. And I think Alexandre will show you nice things about this. Alexandre, est-ce que c'est utile ce que j'ai fait pour toi pour demain? OK, thank you.